So reviewing what we talked about on Friday and reviewing like one big Mama Bahama problem from this section. Says a sketch, but how? Apply the leading coefficient test, which means check out the leading coefficient, but not just it and its sign, but also the degree, right? Not just the sign, but also the degree. Figure out the end behavior. Then find real zeros, which means the x-intercepts, aka set this equal to 0. Then plot sufficient solution points and put all of that together into some sort of graph. We did that all together on Friday, and here's how we did it. For end behavior, that's what the leading coefficient test says. Look at the highest degree term, which is this one.
4.
Notice that n is 4, the degree is 4, and the sign is negative. So an even that's negative is going to, on the ends, be facing where?
Down. Oh.
Down. Too much fun. Facing down, right? So I just wrote down and down. As you go to the right, down, it falls. As you go to the left, down, it falls, right? Okay, letter B says find the zeros. The zeros, I had this, now wait. There's no work on this page for that. Do you guys remember why? Didn't we do it right here? How did we find the zeros? We factored. Factored each and then set both equal to 0. Too much fun in the fun. Sorry. Okay, so setting each one equal to 0 and solving, we found 1, 2, 3 zeros. And the multiplicity, oh yeah, that was like a graphing clue, but we'll go over that in a second. So we found our 3 zeros. I just wrote them down on this page because we had already, oops, too far. We'd already done it. So factor, set equal to 0, and solve. Now, this is what the book would say, plotting sufficient solution points. I just said make a table. But how did I figure out -2, -1/2, 1/2, and 2? It seems super random right here. Remember how I got these x's to plug in? What did I do with these guys? I plotted them and I said, oh hey, who's an x value on the left of that 0? In between those 2 zeros, in between those 2 zeros, and then on the right of that 0. That's all I did. I picked 1 point in every gap. I could have picked -3, it would have been a huge number. I could have picked -1.1, would have been smaller, but it would have been really nasty to plug in. So I'm assuming I'm doing it by hand, so I tried to pick numbers that were fairly easy to plug in, and this one, there was just no good options, so I just chose -0.5. The nice thing with this one is that there was some symmetry, but I plugged into the original function, I found my y values, and I was able to plot, and then, draw a curve through what you guys have left, okay? That was putting together all the huge ideas of section 2.2, besides the intermediate value theorem that we'll get to in a second. The one thing I wanted to remind you guys of is that multiplicity thing. Remember, multiplicity is what's going on with the power of every factor. And when we did this work, we saw that the x was squared, which is the 0 of 0. He was being squared, which is why I had a multiplicity of 2. This guy needed to factor some more to x plus 1 and x minus 1. Each of those were to the first power, which is why their multiplicity was just 1. But how did that translate into the graph? The even multiplicity, something happened, and at the odd multiplicity, something happened. At the even, we bounce off the axis, and on the odd, we go through. So look at our graph. The odd when I went through, then I bounced, then at the even, and then the odd when I went through. Chris, go ahead.
Sorry, can you just go over the multiplicity again? Like if it's like the highest power?
It's the power, not of the original. It's the powers of the factors when you have fully factored the function. So technically, we didn't fully factor right away. We only factored like one step on Friday, and then we had to factor more down below.
Right.
So technically, if I kept factoring, which I maybe should have done to help you see the multiplicity a little bit better, there's nothing further for him. He's just x squared.
Right.
But this one does factor to x plus 1 and x minus 1, which we did down here. Now in its final factored form, we say, hey, what are the powers of every factor up here? So he has a multiplicity of 1, he has a multiplicity of 1, he has a multiplicity of 2 because of the powers.
Right. So, okay.
Now on the graph, any multiplicity that's even, there's going to be a bounce there, and any multiplicity that's odd is going to cross through there. Which is why cross through, bounce, cross through. All right, kiddos. That brings us up to IDT, otherwise known as the intermediate value theorem. But we're not ready for that yet. Let's go check homework. is where you guys are, hopefully, with your color pens. All right, number 8. You could have found this name just from the section. I told you guys we weren't going to talk about it until we came back to class today, but it was the intermediate value theorem. The next few were matching. You guys could have checked the odds, just the even. 10 is there another one in 26? No. 10 is F, 12 is E, 14 is B. And they tended, I don't know, I think they were just using the intercepts, like plugging in when X is 0, figuring out which one had, because they had very different intercepts, so that could have helped. Plugging in when X is 0, trying to find the Y intercepts, that probably was the fastest way to check which one was which. 26 had you analyzing a function, asking you for the degree, which is the 5th power of X, leading coefficient a positive 4. And then it asks you for the behavior. You guys could have done this a few different ways. One way is to use the words, falls to the left, rises to the right. Another way is to use the notation as X approaches negative infinity, f of X approaches negative infinity, and as X approaches positive infinity, f of X approaches positive infinity. Or the other way is you could have said, hey, it's going to do that to the left and it's going to do that to the right. They all say the same thing.
Okay, I just drew a graph and then I did that.
That's cool.
Okay.
But probably with the graph, since it's odd, you would have had to probably do something like that because you weren't quite sure what the middle is.
Okay.
You know what I mean?
Yeah.
Put some dotted in there just because that's not a very precise sketch. But I don't mind the dotted as long as you have solid on the end. All right, this is it done. Any other questions about how the answer could have been written? We did it 3 different ways. All 3 are fine. Okay. 28, super similar. Super similar. I'm just going to show you to the left, f of X. Hi, what you doing? Maybe I won't do that. I'll just do the picture. To the left, it's going to be rising, and to the right, it's going to be rising. If you guys wanted, you could do like a dotted in between. The one place you probably got stuck, or you might have gotten stuck, is 3/4. You can't just use the 3. You have to look at the denominator also. Because what ends up happening there is you're dividing by 4 over 1, which means you're multiplying by 1/4, the whole polynomial. So every term has that 1/4. Every term divides 4. So you might have just put the 3. Make sure you change that to 3/4. But otherwise, the ends both go up. 36, you had to find zeros factoring. Did you notice it was a difference of squares? You could have also solved, I suppose, by subtracting 81 divided by a negative. But you had to remember plus or minus square root. You had to remember plus or minus square root. Oops. Struggle. Letter B is talking about multiplicity, and this is what Chris was asking a second ago. Can anybody explain to me real fast, why do each have a multiplicity of 1? From what we just talked about in class? Yeah. As you look at each factor, each of them are just to the power of what? Well, if nothing's there, we assume it's a 1. Not a 2, not a 3. So we can say each of them have a multiplicity of 1.
Wait.
Yeah.
So, if it's to the power of 2, then you need the multiplicity of 2.
Exactly.
Okay.
But we don't look at the beginning. We look at the factors. So since each of them are just once, then we say 1.
Okay.
Good. Turning points, just 1. That one's a little bit hard, but this one's a parabola, and so hopefully you need just 1 vertex. Just 1 turning point for a parabola. And then I think they let you graph on your graphing calculator. That's kind of lame. You guys could have done better, but that's okay. If you are wondering why I say that, not just because of all the work that we did, but also this is a parabola. Vertically flipped, shifted up 81. But that's okay. Alright guys, here's one of those big mama Bahama ones, right? So let me give you a second. Letter A was leading coefficient test. You didn't have to write the words. You could have just gotten rises to the left and rises to the right. You could have meant it with a dotted. Zeros, you see they're factoring. They factored up here. So they found their zeros to be 0, and positive 3 and negative 3, they just wrote them in order. Maybe your table's a little different, and that's okay. But the question is, do you see how they tried to pick? Now, they picked 2 points in between. You might have just picked 1. Maybe you picked negative 1 and 1 because those were going to be the easier ones to plug in. That's totally fine. I wouldn't have minded that. So maybe you didn't pick that. If you had plugged in negative 1, you should have gotten that point. Positive 1, you should have gotten that point. Which would have been, what, negative 8? Oh, they already have that one. But maybe you picked something like negative 4 on the outside, and that wouldn't be bad, and 4. You would have just gotten a really high value. And maybe if you went to connect, could you have, if you hadn't quite picked the same points they had, could you have been a little bit off? But that's okay. Because remember, I'm not saying you have to do it perfect. I haven't taught you calculus, and I'm not going to. Not until chapter 12, and even then it's just an introduction. So I'm not saying you have to have this entire thing perfect, but I am saying for the plotting of sufficient points, you got to pick something in your table. Get me a few extra points. I would say 1 in every gap. And if you had done that, you should have still gotten at least kind of the oops, I don't know what's going on there. Something magical. I know. But you should have gotten something close. I'm just trying, I'm just making it worse. You should have gotten the W. You should have gotten the bounce here. You should have gotten the crossing through here. You just might have not known to go all the way down. So long story short, as long as it's close, are you okay?
Yes, ma'am.
As long as you did the work, yeah. Is that okay? Okay. I didn't want you guys to think that you had to magically come up with exactly what they would come up with. Let's just get rid of that nastiness. Hey, that's the last one. I think.
Yes.
My document's frozen. Oh, there's one more, and that's the IVT one. Okay. Let's go back to our notes. Let's write just a little bit about IVT. And guys, it's really not meant to be a super hard thing, okay? It's not meant to be a super involved thing. We'll go ahead and check number 94 tomorrow. Because most of you probably just skipped the IVT one, and that's okay, I said you could. So we'll go ahead and just wait on number 94 until tomorrow, and then Mario's going. So go ahead and write what you see, kiddos. There is an example on the next page. I'll try to show you the idea of what's going on. If you want to grab out your calculator, you can. I'm not sure if we'll totally have time to look at the calculator part to it, but we will definitely tomorrow when we check just that one problem, the last problem of homework. Bless you, bless you. And tomorrow when we go over that last problem of homework, bless you, I will also ask if there are any remaining questions, okay? So if you want to look over the evens, anything you missed, if you want to look over the odds, any of the ones you weren't able to figure out. Nope, that's not you. Where are you? There you are. Lo siento. I'm opening up my graphing calculator as you guys write that. We'll give you the height example in just 1 second. I think I have it in my calculator. Okay. You guys ready? As you guys finish writing, let me go ahead and give you my height example. I'm approximately 6'2". Height, right? My question to you is, was I ever 4'1"? You sure? Me? I'm 6'2". I was. Was I 4'10"?
Yeah.
Was I 5'1"?
Yep.
5'2"?
Yep.
5'5"?
Yep.
Hey, I'm getting to all your guys' heights. 5'10"? 6 foot?
Yes.
I was. I feel it. Maybe you will be one day. And maybe not, but maybe that's a good one. Okay, coming back. Coming back. Okay. How do you know I was 4'1" at one time in my life? Did you know me when I was 4'1"?
No.
No, I didn't know you either. You weren't around. How do you know I was 4'1"?
Everybody has to go.
Everybody has to grow. In your head, you just thought, and without even consciously thinking about it, you thought of IDT. In your head, you literally just used the idea behind IDT.
Oh.
Because I'm 6'2" right now, and I was born something a lot smaller than 4'1", right?
I hope so.
I hope so too. I was a big baby, but it wasn't that big. Full head of hair. Coming back. So, when I was born, I was, I have no idea, something. I was small, and now I'm tall, right? I had to go through all those heights because, ready, look at the application. Because height is a continuous function. To get from one height to another, you have to go through everything in between. Intermediate means in between. It's not beginner, it's not advanced, it's in between, right? Intermediate value theorem. Value talks about y values. Anyway, there's a whole thing in calculus that says if f is a continuous function, there exists a k within f of a, f of b, such that f of c equals k. Anyway, whole thing. Calculus kids have to memorize. You guys don't need to memorize, it's just an understanding, saying to get from one point to another, from one height to another, from one y value to another of a continuous function, you have to somehow hit everything in between. So, if a function goes from a positive number to a negative number, from one x, plugging in one x, you have a positive y at one x value, and a negative y at another x value. The question is, as long as the function is continuous, must it hit 0 in between? Yeah, to get from that height to that height, to get from here to there, it has to go in between. Now, do I know exactly how it goes in between? No. I have no idea how it goes in between. I don't even know how many times it goes in between. But a function goes from left to right. There is no like this because the axis still, no. Right? That's not a function because that fails the vertical line test. So any function that would pass the vertical line test to get from a positive to a negative has to hit through 0. Okay, so what if it goes from a negative to a positive? Still has to hit through 0 somehow to get from that negative to that positive as a function. That's the idea. That's IDT. The end. How do we actually do it then? Okay. Ready? Example. And this is super similar to your number 94?
7.
Yeah, that one. Whatever one you had with IDT. Maybe you had 2 of them with IDT. Okay, this is super similar. This one says, use the intermediate value theorem to find out. Intermediate value theorem. All that we're stressing about is sign change in the y's. That's it. You might want to write that down. The only thing that we're using IDT is we're looking for a sign change in the y values. Because if we see a sign change, we have to say, oh, there has to be a 0 in between. Because all polynomials are continuous. We wrote that down at the beginning of our notes. All polynomials are continuous. So for a polynomial to get from a positive to a negative or a negative to a positive, there has to be a 0 in between. So kiddos, I'm going to take this function. I'm going to put it into my y equals in my calculator. Actually, I already have it there. If you want to just pay attention to my calculator, that's fine. It's right here. You can just pay attention to mine if you want. So I've gone ahead and put, sorry, I'm trying to get this out of your way. Oh, I can. Okay. Take that function, put it in my calculator. How can we see the IDT at work? Graphing? No. Tables. So if you guys remember, second window gets us the table setup. In my table setup right now, I have it starting at 0, going by 1s, automatic. You can do all of this with your graphing calculator handbook. So in the table, remember looking for a sign change. Do you guys see any sign changes?
Yes. Yeah.
Where?
1,
In between 0 and 1?
Yes.
See, there's x's. I see the y's go from a positive to a negative. And in between 3 and 4. Right? Now hold on. How many zeros can this guy have? 3.
4.
He can have 4. Maybe I should keep looking. What if we scroll down a little bit? Has anybody scrolled down? Does it look like it's getting any more? It's not getting closer to 0, right? Okay, that's not good. Or if we come back this way. Ooh, we would have missed one, I think. Because, you guys see this sign change? So we had in between 3 and 4, in between 0 and 1, in between -1 and 0, and I bet if we keep going back, we'll find the fourth one. There it is. We see where all 4 are. Now, can we say exactly it's -3.127? No. But we know there's something in between these two numbers. So if I was to go to my graph, I'm looking here for a 0, I'm looking here for a 0, here, and then at 3 and 4. Now, what if I was to change my table set to be by 0.1s or 0.01s? Could I get any more precise as far as where the 0 is? Yeah. So I'm starting at -4. That's the first place, -4, -3, there's a 0. I'm going to go by 0.1s now. Can we get an even better picture of the 0? Oh, no. Down even further, huh? So I'm looking for a sign change, right? Ooh, you guys see a sign change? Mm-hmm. Right here. I know not only is it between -3 and -4, I know it's between -3.1 and -3.2. That's a pretty good approximation without having to use my graphing calculator, my actual graph. Now I could go one step further, and I could go to this positive and I can say, hey, now let's go by 0.01s. Right. Just showing you how IDT works. And maybe that's how the programming works. Somebody had to understand this principle in order to get your calculator to be able to tell you the zeros. I don't see a sign change, I don't see a sign change, I don't see a sign change. Those of you guys that don't have a computer calculator might be going a little faster than me. Getting there, right? Oh my goodness, come on. There we go. See the sign change?
I see it.
Could I keep doing this? 0.001, 0.0001, 0.00001?
Yes.
The calculator, when it finds a 0, only keeps so many decimals, right? So maybe when it finds the 0, it's not actually doing math like factoring. Maybe instead it's actually using this approximation technique called the IDT. Interesting. Now, if we were to actually find a 0 on the graph, the one that's around -3 and specifically around -3.11, we could go ahead and just go to our graph. I have no idea my window, but I think I'm good. I could go ahead and hit the trace and say, hey, I need to go around -3.11. That's just trace, that's just getting somewhere on the graph, that's the one I want. Next second, calc. Let's figure out or watch the calculator at work. I'm going the wrong way. We know it's around -3.1. There we go. And we see it come up with an answer, but my question is, where did that answer come from? Not outer space, someone programmed that ability in. The actual 0, -3.112943, but there are more decimals, so maybe that's just an approximation, and they went by 0.0000001s. All right, cool kids, that's IBT. We'll look at that homework problem tomorrow. Basically, they're just saying, having you write down what we said in words. For instance, we wrote down from our table, if you guys want to actually show some answers, that there's going to be zeros in the interval -4, -3, -1, 0, 0, 1, and 3, 4. That's all you have to write for your answer for letter A. They just wanted you to write down where you see the sign changes. And then letter B, when we got a little bit snazzier, we were able to figure out, and I'm just doing an example for the first one, we were able to figure out the in between technically 3.2 and -3.1. Then we were able to get even further, -3.12 and -3.11. You're just showing, hey, I can zero in on these zeros too. All right, cool kids, that's section 2.2. Thank you for letting me finish it up, but not only that, but also check the evens. But we do need to go ahead and introduce section 2.3. This homework is due on Wednesday, but I'm pretty sure most of you could get a good start on it tonight. You're finishing up the IBT. Does anybody have how many IBT problems there were? Sorry, intermediate value. Just one. Okay. So you're just finishing up that one IBT problem. And I have the answers all ready to go for us to look at tomorrow, just to make sure that you guys understood it. But otherwise, you want to start 2-3 because it's review. You want to start 2.3 because it's review. And you need to be reminded of it, for sure, for sure. And you need to be warned about the different common mistakes that occur in this one. For sure, for sure. But it's one of those that most of you got down pretty well when you were in Algebra 2. And it's going to be helpful in lots of different ways. As we get, or as we see harder polynomials. Because for those of you that did do some factoring and homework, which hopefully all of you did, the factoring was pretty easy. Because in 2.2, any ones where you had to find the zeros by factoring, there was always a greatest common factor that came out, so that you only really had to factor a quadratic. But that's not how, sadly, all polynomials are. Okay. We're starting off with a problem where it says, hey, guess what? Here's the answer. This guy can be rewritten that way. Use long division to verify how. Now, long division, really quickly, just so you guys don't get confused. Long division is the same thing as polynomial division. Long division is the same thing as polynomial division. Not in general, because, I mean, long division with numbers, that's not with polynomials. But if you're having polynomials, doing long division, otherwise known as polynomial division. But in order to do this division, let me go to a new page where I can have more room. Sound good? So here's our example. We need to show that the left is truly equal to the right. Do you guys remember, just with fractions in general, before you even get to the polynomial on the board, let's see, what could be some sort of improper fraction that you might need to use long division for? How about something like 47 over 6? That sounds good. Okay, do you guys remember how you would make this into a decimal? A lot of you like decimals. How would you make this into a decimal? Or into a mixed number? Who goes in the box? Good. 47 goes in the box, 6 goes on the outside. True? Coming back to that in just 1 second. So let's go ahead and use it in our example. So who's going to go inside the division box on this one? Good. The top one. Now it's usually a safe thing if there are missing terms in the polynomial. Not that they're not supposed to be there. They're not supposed to be there. I should say not that they're supposed to be there. But it can be helpful to put zeros to hold the place. In synthetic, we have to put zeros. In long division, it's our choice. But if we don't leave a space for it and an x cubed term pops up, we'll be in trouble. So I always make a space, starting at the fourth, making sure that there's a space for every single possible degree. Now, who's on the outside? I'll pause really quickly. Some of you are like, why are you teaching long division? Synthetic is so much faster. If you remember synthetic, that was easy. Here's a dilemma. This guy, you could never do this division with synthetic. And here's the reason why. He's an x squared. Synthetic division only works when you have an x alone. So for those of you guys like, let's do synthetic. Okay, we will, but we can't. Not all the time. We have to cover the method that always works. Now, we have our top one in. We have our bottom one out. Here's a, I don't even know where I first heard this. You can think about like someone with a sword. If you chop the head off, it drops down. People actually talked about a guillotine. I don't know what teacher it was. Some teaching workshop. Anyways, kind of silly, but you just think about this one drops down. Slice it, that one falls off, this one's still. Anyway, it's kind of morbid. But coming back. Let's talk about the numbers before we go back into polynomials. Let's talk about the numbers. Question. How do you do division? Yeah, how many times does 6 go into 4? None. How many times does 6 go into 40? 42.
No.
47.
Yes.
7 times, right? 6 goes into 42 7 times, and that's the highest, the 6 and times 8 is 48, right? Now, so you figure out how many times does this go into that. You have the 7, so then you go ahead and multiply down, right? And you subtract. We'll come back to what happens after that in just a second. This marker is kind of trash. Okay, but this one's kind of hard because I do have a binomial. But if you look at this, this has x's and that has x's. Look at the outer, okay? How many times does x squared go into x to the 4th?
Twice.
Kind of. But not like 2 times. X squared times. Does that make sense? 2 times x squared is just 2x squared. That doesn't help. But x squared times x squared, that's good. Now question, why am I writing down 2 things though? I have to distribute. I have to distribute, right? So x squared times x squared is x to the 4th, 5x squared. I line them up because I need my terms to be like. But in division, how do we go down? Subtract. Here's where you might kill seals. Don't do it. Not only do you have to distribute, sorry, my throat's dry. Do you guys hate that when you have a tickle in your throat?
What?
Got a cough drop. Thanks, guys. Trouble having a profession when you have to talk and your voice isn't good. Okay, ready? We had to distribute, true.
Right.
But now as we go down, what do we have to do with this guy? We have to distribute also. We have to distribute our negative. We have 2 different terms that are being subtracted. They both need the negative brought in. You have to be so very careful with that. These 2 cancel. Perfect. Negative 3x squared minus 5x squared. No, I don't think we're going to need that guy. Maybe we'll need that guy. I just bring everybody down. Question, how many times does x squared go into negative 8x squared? Distribute.
I get it.
Careful. You must distribute the negative. And negative times a negative is a positive. Bring in the negative. Gotta fit the signs. Negative 8x squared plus 8x squared?
0.
What's this? 39. Now, let's review with our number real quick. Up here on the board. Could I call this a remainder? And the answer is yes. But do you remember how we advanced from that? That was elementary. We then started making it a fraction saying, hey, there are 5 out of 6 pieces left. We're going to do the same thing here, but this time it's 39. I put a plus just to indicate it's positive. Out of. Kiddos, how does that compare to this? Right? Be real, just quietly. Okay, guys, we're gonna write this down tomorrow. No stress. Long story short, division can actually show us a lot of things. We'll write that down tomorrow. My question is, how would you start doing division on this one?
You put x cubed plus 125.
Think about it as the top, right?
Yeah.
Okay, and the bottom would be?
X plus 5.
Good, so who goes on the inside?
X cubed plus. Wait. Yeah. X,
My warning though, don't just put plus 125. What did I tell you to do?
oh, x cubed plus 0, x squared plus 0, x plus 125.
Now,
X cubed.
question, just for those of you that might want to start homework tonight, listen. Can I do synthetic from what I said a second ago? Can we do synthetic with this one?
Yes.
And we are. So let me remind you to go fast. We'll practice it tomorrow. With synthetic, do you remember that you use the coefficients?
Yes.
I think so.
But who goes in the box? Not the whole thing. Not the 5. Pause. It's the 0. You plug in the opposite sign.
Where does his take so long?
I'm just showing it'll be in the notes for you guys to see. You drop down the 1, then you multiply. Then you add. You multiply. Then you add. You multiply.
Oh my.
Magic. Then you add. Do you remember what this last one represents?
Remainder.
Remainder. And this is your answer, or what it should be, after you do all your work.
I'm so happy.
Cool kids, we have to practice it tomorrow. It'll be fun. We still have 15 seconds. Jacob, your question before I let him leave.
On the homework, when I didn't get one, I went to Calc Chat, and it looked like that. It looked like,
Really?
yeah.
Make sure you were in the right section, but otherwise, if you can check one more time tonight, take note of it, because I need to figure out the mistake. Thanks, bud. Bye, guys. Thanks for putting up with my cough. See you guys tomorrow.
Look at that job.
Last year, vision problems, and those 4 rows.
Bye, Lainey.